We have heat source, and then for purposes of simplification they have taken it circular, so that the effects are not there. So, we have so much of P, there is A and length of contact, and this is exactly what I was trying to tell you when I pointed out this experiment with the thermal conductivity flask, which we have all done once upon a time, long ago. I have done it in 1960. That shows how young I am, but physics has not changed, physics has remained same, our understanding and modeling has changed. Now, you probably do not even need to make the experiment, you have an animation and all the things are modeled, and the model is fairly accurate. Somebody has tried it, and then what do you call, they have come to the conclusion there is nothing wrong in the modeling, because the model is based on actual experimentation. They also know, similar to what I have seen there, I have shown you there, they know the conductivity, they know the cross section, and most of them are made typically to make it very convenient, to be visible in a class. Usually they are around 4 millimeters diameter. Earlier it was somewhere between what do you call, probably it is between 1/8 and quarter inch and 1/8, probably it was 3/8 of an inch or something like that, I am sorry, 3/16 of an inch. So, that can be easily checked. So, if you are curious enough, go back to the internet, and maybe in YouTube you can find it, though I have it with me. I want you to search, go on to the internet, find out this experiment about how to find out comparative thermal conductivity of 3 materials, which is usually done when you are around 11 years or 12 years old. So, they are all simplified things like this here. You have seen this homogeneous heat conduction. There is a star there, I will read the star about it later. It just generally it says that star refers to area of cross section is uniform throughout the heat flow. You understand, no? Area of cross section is very critical about it. And coming back that Fourier's law about it, saying thermal conductivity, as we know, has been defined in the table as watt per meter degrees centigrade, and then length of rod in meters along the heat flow path, cross section in meter square perpendicular to heat flow path, temperature of source and temperature at ceasing. That is how the other thing has been done. It will be the same whether T1, T2 are expressed in degree or Kelvin, because 273 gets cancelled. Thermal conductivity depends on the material, that metals are generally good conductors, insulators are not. Certain similarity to electrical conductance. So, copper is an excellent heat conductor and resin is a very poor one. As in the case of electrical conductivity, K one more time is a function of temperature. You understood, no? Rather, I have given you, I started with the example of the incandescent bulb. So, a lot depends on the way the thermal conductivity and the way the current flows through, and as it goes hot, what happens. You too would have noticed, if you are one of those people who are before ban the bulb agitations. A huge in Sydney Opera House, they had the ban the bulb what do you call launch around 2 or 3 years back. I understood it was a big event. They even switched off the lights, and every year we have this how to save energy, switching off the lights. Lot of incandescent lamps, surprisingly, when you switch on, they fail. It is a very irritating, very rarely they fail when it is already working, except there is a voltage fluctuation. The moment you switch on, suddenly inrush current comes. In case there is any already some deterioration of the material or anything, it fails automatically, which is a little related to this K. The thermal conductivity is also a function of temperature, but however, it is very low, because typically it is less than 0.1% per degree centigrade. So, we are saved at those things. It is convenient to express the formulas for heat transfer in a similar way as electrical networks. So, in the case of electrical network we have a delta V saying, is it not possible for us saying this thermal resistance into the power will give you the temperature difference. Sorry for the interruption, we will edit it out. So, we see here that it is possible for us to define a thermal resistance just like we have conductance, and good old Ohm's formula or Ohm's relationship can be used, just like resistance is equivalent to voltage by what you call current Vi, and similarly an IR drop, saying we have a thermal resistance and then we have the total flow of this thing, and then what will be the temperature thing. So, once you do that, things like degrees centigrade per watt for a device like this can easily be defined. Now comes the next level of thing, which I thought no, I should leave it to you for saying how to what do you call model this. This next expression you have seen that. This is what I was telling you, reading it out. Same form as Ohm's law, one simply replaces power by voltage, and I am sorry the if you replace current by the power, then the voltage by the temperature difference, then the thermal resistance is equivalent to what do you call the thing which is shown by L by K into A, which is shown there, can be expressed by the equivalent circuit like this. So, it is possible for us to now start working on this example. Now, I sort of jumped through and then I showed you. The analysis is now extended to, can we have radial and can we have spherical heat flow. So, if you see this heat sink, my suggestion is kindly take whatever heat sink is there with you, and then you take the area here and you take the area of cross section of this. So, in this case this is a 2 mm by 70 mm. You understand, no? We have 140 square millimeters and we have 1, 2, 3, 4, 5, 10 fins on this, 10 into 140, that is the area available for us for enable to for conduction, though this is very, very high. You understand, no? This is 70 into 50. This is very high compared to that 2 into 70, 140 into 10, that is only 1400. Here we have 50 into 70, which is 3500. So, that is typically about 2.5 times of this. Now, we come to the next thing. To enable conduction, why can't we make this wider, but then we will end up with the problem of not having enough space for the air to pass. This is where the complications or the modeling becomes effective. You understood, no? So, take this some typical heat sink what you have, and imagine if something were to be mounted here, directly it is attached to power device. Typically it could be a heat bridge. In this case we had direct access to these power devices. A lot of times we may not have access to these devices. So, you may need to pack it up with some other material. Imagine the whole thing is covered and this is the case itself. Imagine this is the case itself. Okay, it is a corrugated case like this, and then you need to pass that thing. So, we need to find the conduction. Usually because of the large aluminum conduction and all that, it comes here, and when it comes here one more time we still have this problem. Only a small area is available out of the 70 into what you call 50, 3500 square millimeters. we still have only a small area which typically represents this only. This is where conduction calculations are very, very critical. Now, the next picture shows saying in the case of a radial heat flow, you will notice that area is continuously increasing, but we have known small d we know, and then if you know small d and this thickness b, d into b is at this area. As it goes out, we know the typically you can have a definite integral between what you call like internal radius to external radius, and then by integrating the whole thing we end up with a beautiful expression which can readily be used. This follows that Pentium cooler which I have shown you. If you see that radial modeling there, base of it is, if you see that earlier first picture I showed you, there is a what you call circular heat sink, and then at the base of it the square pad is mounted, and then from there radially we have heat sinks. At those points when you are calculating the heat sink what you call the way the heat reaches the end point, you will be able to use these expressions easily, and this is already what is built into most of the CFD or FEA packages. They use these known correlations, but two things very important is your geometric model what you present has to be accurate. You cannot, I have just just like that I have tried to, this is only slightly better than my feeling with my finger, not that fingers are bad. See, I can by practice, if you take it to a workshop, he will feel it like this and says, sir, this must be probably what you call 1.6 millimeters, because he knows typically such devices there, the practical thing is 1.6, and if you measure it, it will exactly be 1.6. So, things like 1 by the k contains the same thing which we have seen there into 2 pi by b, this natural logarithm of d by d can be calculated as per equation. These analytical methods can be easily used for known geometries. Okay. But I am not very sure where you will get, while I have shown you a rod like typically a pin fin, I am not very sure where then I have shown you what you call, if you have a component mounted at the middle, how heat can go away radially, and then after that it can go to a pin fin. So, I have pin fins, then we have a circular base, and or even if you have a square base you can approximate it. This comes much more important for, you see the beautiful note that is given here. Inhomogeneous heat flow becomes much more complicated, may escape an analytical solution. Practical case of heat conduction in electric equipment can be approximately given by using these combinations. A source of heat is placed on a top of a large body, heat will flow radially away, that the heat density is nearly the same for all points in a half sphere of radius away from the source, so that uniformly at the same rate it is going. So, we have a spherical heat flow where they have already approximated and given this. 2 or 3 things can happen. The temperature gradient may change, and it may be other losses directly at various points. Even in the case of heat sink, even a simple parallel heat sink, we have assumed that this cross section is constant, but we have forgotten that the ambient temperature varies. At the tip the ambient temperature is different, at the base it is different, and as it goes further the behavior of it obviously it is valid only in the case of a pin fin which is insulated outside. So, no heat loss is there by any other means including convection to the ambient. So, we have this what you call things about how to model these things. The next picture in that nodes takes us to maybe I will start here and repeat it away. We have noticed that the so called heat sink is nothing but a what do you call a bridge or a heat what do you call conductor away from the source. Now, you need to pass it on to the cooling medium. I have given you an example of the circular tubes which are used in air conditioning and other things, where you can have radial fins inside and you can have radial fins outside. So, when you have this radial fins inside and outside, that behavior can be modeled easily. Now, in the case of heat sinks, that similar modeling has been done here, because these are also have been that like this, saying you need to take away heat by convection. By definition, convection depends heavily on position change. Understood, no? The molecules change their position. That is why heat and mass transfer are related somehow. And then, as if things are not what do you call good or bad enough, the moment you heat some portions of a fluid, it expands and buoyancy is created. That is what creates natural convection cycles or thermal cycles inside, which you can see in the thing. On a hot day, you can see so called mirages on the street. You do not see all that what is shown in the comic characters, no? Saying somebody is crawling in the desert and in the distance he sees lot of entertainment going on. That is not what happens. What happens is, due to total internal reflection, you see something which seems to be reflecting the top surface. So, if you have trees, you see something. If you have any objects, rocks, you see an object. So, you are likely to mistake it for water. So, this is all exclusively created by thermals and the variation of refractive index depending on the nearest refractive index. So, something called the total internal reflection, what you see in the case of your prisms and all, will take place without actually there being two media. Total internal reflection typically will have two media. On one side we are all familiar, we will have water, another side air, or we are familiar, we have glass and we have air. But in this case is air versus air, still one that causes is the small temperature difference, which causes all that various types of phenomena. What happens is, air near a hot surface warms up, expands, rises and pulls new fresh air along. This process is called removal by convection. Air is a very poor heat conductor. I have shown you there, it is not very great actually. In the table when we went back, air is a very poor this thing, and in fact all insulating materials depend heavily on air. You have seen this, no? Still air. Even water also does not seem to be very great. It is only 0.6 what do you call this watts per meter degree centigrade. Not very what do you call encouraging. Yes, compared to aluminum, that is if you divide this by that, you will get a really horribly some 300 or 400 times less conductive than air. Is a very poor heat conductor, and then all your insulation depends on trapping air in closed cells. So, typically if you take expanded polystyrene or polystyrene foam or PU foam, you have cells inside. If it is closed, it is very good because it will prevent ingress or condensation of moisture, and air is the one that creates the insulation. By themselves, no, there are no insulating materials as such. All insulating materials depend on air as the insulator. Same thing with your jacket. And I am sure you have noticed when it gets waterlogged, it becomes ridiculously cold. Any insulation, including mineral wool, which is used in your boilers or even which is used in now called the electrical geysers and all that, once water gets into that, 0.02 suddenly becomes 0.5, and then we are lost. From there onwards, it is a very short jump towards problems. Heat is transferred to the air by convection. This convection is aided by swift airflow. A vertical surface is more efficient than a horizontal one. The vertical fin allows good airflow and therefore facilitates good convection. A horizontal fin restricts the airflow and is poorer. A multiple fin arrangement by which you can increase the total surface area that is available. I have just pointed out to you in a practical example. You can't really keep them close, very close. And again in that statement you will notice that a lot of it depends on the speed of the airflow, swift airflow. You have seen that, no? Airflow should be fast enough. That is, the already little what you call warm air, warm molecule should be replaced by colder one, so that directly on the surface you have all these effects. So, people have worked on it, and even today that modeling is critical, and as I said, the corporates who manufacture these heat sinks and all employ people trained by us, okay, and then to make the model clearer and better and all that. So that if somebody were to sell you a heat sink, all they need to do is just make one model. If they increase the depth, they have the answer, and if they increase the length, the answer is there, and if they increase the spacing or increase the width, the answer is there, which is all based on use of the modeling things, which I have shown you earlier. As we go down, all the three conditions are shown here. So, the next slide points us to the as air moves upwards along the fins, it gets heated. The upper part does not get the same cooling as the lower one. High narrow fins do not have the same high efficiency as low wide fins of the same surface area. Temperature in the fin due to conduction resistance can be neglected, that is, the total fin is there, and then we end up with one more time Hc here. Just like as we had heat transfer coefficient in conduction, we have a heat transfer coefficient in convection. Our whole problem is how do we get that Hc, heat transfer coefficient in convection. It is not yet, it is not that easy as it looks like. Good approximation can be given by the following formula. Understood, no? They have given here alpha is equal to, in the case of a vertical plate, and then this should be of course bottom sided cooling, how much should it be, and top sided cooling, and how much, it should be 0.6, there is a mistake. These things partly due to understanding of the physics, partly out of experimentation, they have got into these beautiful figures. Okay. At this point, I will try to probably stop here, and then in the next lecture I will get back here again and then try to see how best whether we can solve it, and we can try to apply it for a small heat sink like this. So, thank you, and see you again next time.